All right, now this is the last thing that we have to discuss when it comes to simple harmonic motion, and it's continuing on with the discussion of wave equation, in particular, moving on to the idea about energy. So we already have these equations for the position, velocity, and acceleration. Well, now we can actually figure out the kinetic and potential energies as functions of time. Now recall that we already talked about what the potential and kinetic energy should look like as functions of position. For example, if we have a spring oscillating side to side and we want to know what the potential energy is with respect to the amount that the spring has compressed and elongated, we can look at the equation that we have, the 1 half kx squared, and figure out that it should look parabolic. It basically ends up looking like the path of a pendulum. But that's not what we want. We want as functions of time this time. So what we're going to do is pretty much look at the graphs that we have for velocity and position in particular, and see how those equations relate to the equations for kinetic energy, or sorry, what the graph and the relationship correlates with the equation we have for kinetic and potential energy. So for example, kinetic energy is going to be 1 half mv squared. So what we end up having, if we have a velocity like this, at each of these 0 points, when the velocity is 0, because of 1 half mv squared, the kinetic energy is going to be 0. So at this point, the kinetic energy is going to be 0. At this point, it's 0. It's 0. It's 0. It's 0. And then we know that when we do the kinetic energy, because it's 1 half mv squared, every time it hits a maximum value, regardless of whether it's a max positive or max negative number, it should be the same thing. For example, velocity that's 4, let's say 4 squared is 16, negative 4 squared is also 16. So every time this velocity hits either a minimum or a maximum, my kinetic energy is going to hit a max. So it's going to hit a max at this point, it's going to hit a max at this point, and this point. Once again we kind of connect the dots, so we draw up, 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 and we end up with something like that looks like this. Now notice the kinetic energy still kind of looks like a trig function. It kind of looks like a cosine curve, but it was shifted up, and that's actually something that's extremely important to remember, is that with these energies, they don't go negative, they're scalars. Because of that square term, we should never have the energy dipping below the 0 line. This is actually really important because when they give you the graph in order to draw things in, they know that it shouldn't go to 0, but they're going to test you by giving you a graph that both has a positive axis and a negative axis. So they're going to try to trick you thinking that maybe it does go on the negative side. You just have to remember it never does. So it should still kind of look like a trig function, except more like absolute value trig function. The other thing to point out is here, if I looked at the graph for velocity, it's very clear when I complete one period. Here, it's kind of trickier. It does kind of look like it repeats its cycle at this point. So a lot of times with the energy stuff, it's almost going to look like it's got a higher frequency. I think technically the period is the same, but it's a little bit like weird because it's hard to compare a sine curve with a sine squared curve. I could do the same thing for potential energy. Pretty much works the exact same way because of the kinetic potential being pretty much the same format as kinetic, with the whole 1 half blank x squared. So if this is our displacement, once again, this is going to hit zeros at the same point as the displacement. It's going to hit maximums at the same point. I'm going to make them a little higher. And the negative amplitudes are going to be the same maximum. So it's going to connect the dots like this. And again, it actually looks almost exactly like what we had for the kinetic energy. Once again, the period is sort of kind of looks almost like it's gotten halved, like it's twice the frequency, but it's once again looks like a cosine curve just above the x-axis. So altogether, these are the graphs that we have. Again, while this is going to be the common distribution where you're probably going to start with this type of displacement graph and then it's going to go to this velocity and acceleration, yada, 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 it's important to always remember that this displacement graph can be changed. They could switch this displacement graph so it could actually be a sine graph, a negative sine graph, negative cosine. And you should be able to know how all these other graphs will change accordingly. It is also important, I didn't put it in here, but mechanical energy. So if we actually graph, put the kinetic energy and potential energy together, I'll overlay it right here. So when this hits a peak, it should go down and it goes up like that. The mechanical energy basically skirts the top of this. So it's going to go flat. I didn't really draw that first line good, but the mechanical energy should be a flat line because in a case without friction, in the ideal case, the energy doesn't decrease over time. Now, I just said that this is true for the ideal case, but what about when there's friction? So this is actually an interesting thing because we know that when there's friction involved, things kind of get a little bit weird. A lot of times in lab experiments, you may have heard me mention that while sometimes it's good to try to have things go for as long as possible, that way measurements of things like time become a lot more accurate. You kind of have to make sure it's balanced with the fact that friction becomes more of a factor the longer things run. A perfect example is when you're doing a momentum experiment where you're trying to figure out the speed after two things explode away from each other. You need to figure out what their speeds are immediately after the crash. Now, if you have it so that the distance is really short, so that there's no, like, the amount of friction that the car experiences is really low, then the amount of time it takes for it to cover that distance might be too short for you to get an accurate time measurement because you'll be hitting that timer so quickly that your reaction time becomes too big of a factor. So you might think, okay, well, let's elongate it to 1 meter. But you might find that the friction becomes a lot more noticeable as you can clearly see the car slowing down as it reaches that 1 meter to the point where it may just barely cross over that meter point without, well, like just barely making it across. So in that case, now even though your time measurement is a lot more accurate, the friction has slowed the object down so much that it's no longer equal to the immediately after the crash. So you end up kind of throwing off your calculations. So you've probably noticed that in some of those labs that you kind of have to strike some sort of balance of making things go for as long as possible so that time measurements and distance measurements are accurate, but not long enough for friction to be a factor. Well, it turns out that if we include friction, that actually doesn't really change much for our simple harmonic motion oscillators. I mean, yes, the amplitudes of these values, the max displacement, the max velocity, the max acceleration, and energy values will start to decrease over time. If you've ever seen a pendulum swinging, you'll see that it starts off swinging close to what looks like its max value, but then you'll notice over time, every time it swings, it kind of goes a little bit lower and lower to the point where it's barely swaying side to side. So we can guess that the amplitude should be decreasing for all these graphs. However, there is one question that we should ask ourselves, and what happens to the period? Is the same effect that we had before in that hypothetical lab experiment the same here, where as these pendulums and as these spring systems oscillate over and over with friction slowing it down, is that going to affect the period? Well, it turns out no. If you think back to the equations we have for period, the period for a spring is 2 pi rad m over k. Nowhere in this equation is max displacement, velocity, acceleration, or energy taken into account. Mass and spring constant are the only things that matter because mass and spring constant are constants, essentially. They don't change over time. So regardless of the fact that friction slowly takes away the energy and slowly makes the object not go as high up, the period doesn't change. Same thing kind of applies to the pendulum. So the period for a pendulum is given by 2 pi rad L over G. And of course, this is the approximation, but once again, we have something that doesn't really depend on amplitude or energy. It's length and gravity, neither of which are going to change just because there is or isn't friction. So the period of these graphs should stay the same. But what we're going to end up having is, if you're being asked to graph this, you want to make sure that every time it reaches its one of the peaks, it gets lower and lower each time. So a perfect example is this. This is our acceleration graph. So if I did acceleration for an object experiencing friction, it will look something like this, where it hits its peak. Then when it goes down to the negative amplitude, instead of reaching at the negative amplitude, it's a little bit lower. Then it goes up and it goes even lower than that, and lower, and it slowly kind of funnels into here. And you'll see that the amplitudes kind of follow this this exponential curve, decreasing, getting slower and slower to 0, though it gets incrementally closer to 0. And if you actually have a pendulum running, you'll see that it still sort of sways ever so slightly, even after it's been running for a really long time. All right, so here I want you to try to make a graph based off of the previous acceleration graph that I showed you. So pause the video, work yourself, and we'll go over in a second. All right, so what I'm going to do is, for these graphs, I'm going to start off with the acceleration as a foundation. All right, so let's see. First, what I want to do is plot the points. So just like last time, I'm going to point where the potential energy is going to be 0 and when it's going to hit a max. Now, of course, I don't really care about the actual value. I'm only using this graph as a guide. So don't think that when I do this, that I'm saying that the max amplitude for the acceleration and the max potential are the same value. But I know that the acceleration reaches its max at the amplitude, and so does potential energy. So every time this reaches a max value, whether it's a positive max or a negative max, I'm going to put a point. So it starts at there, and then every time the acceleration goes to 0, that's the equilibrium point when the potential energy is also equal to 0. So my points are going to look like this. Every time my acceleration goes to 0, so does my potential energy. Anytime my acceleration goes to a positive amplitude or a negative amplitude, my potential energy goes to the max as well. And then what I can do, once I have this all, I can draw a line that goes through them. And then when I get rid of that, this is what I end up getting for my potential energy graph. All right. Again, looks pretty much exactly like what I had before, except the amplitudes are slowly decreasing over time. All right, kinetic energy, I'm going to do pretty much the same thing, except I have to kind of flip everything. So for example, when I said before that the acceleration hits a max at the amplitude, well, we know that kinetic energy reaches a 0 at the amplitudes. So the first point is going to start there at 0. And then every time the acceleration goes to 0, that's the equilibrium point, which we know kinetic energy reaches a max, which is there. So I do that same exact thing I did before, where this time, every time the acceleration reaches a positive or negative max, I'm going to put a point at the 0 line at the equilibrium, and anytime the acceleration reaches 0, I'm going to put a point at along this dotted line. So my graph, my point should look something like this. And once again, I can connect the dots, get rid of that overlay, and this is what the graph should end up looking like. Again, looks like a sine curve, but a sine squared graph, all positive, but slowly decreasing over time. Now, the last question is, what about total energy versus time? All right, so what I'm going to do is I'm going to start off with my potential energy and overlay the kinetic energy right on top. You'll notice that if I drew it properly, it should, for the most part, kind of go in and out, essentially. Once one hits a max, the other one hits a min, and so on, so on. I did a fairly good job, but you could see over here that some of these points probably could have been shifted. So how do I find the the total energy? Well, what I'm going to do is just draw a line that goes through the tops of the points, like that. So this green line is my total energy. Now, I should have pointed out, well, I should clarify that the total energy, if you notice, it talks about the mass spring system. Remember, the way that they describe a system, it's supposed to tell you what type of energies are involved. Objects like a mass can only have kinetic energy, and springs can only have potential energy. So what this was basically saying is that these are the only two energies that I'm allowed to look at. I am not allowed to look at energy caused by or lost by friction. If I was able to include that, then obviously this graph would stay flat because total energy of all types of energy remains constant. But because they specified that it was for the mass spring system, I have to make sure that friction is not being taken into account. And that's pretty much it. So again, you should be able to make these graphs both in the ideal case and with friction. And you should be able to do it for the motions of any different starting setup and also for the energy for any different starting setup. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.